So in this overview talk of yesterday, the main result of this series of talks was already presented. That is the existence of exactly 52 possibilities for the Sato-Tate group of an abelian surface. And as I said at the end of my talk, a direct approach to resolve this problem is to compute images of L-adic representations attached to abelian surfaces and then follow the steps of the construction of the Sato-Tate group that I described yesterday. And then, so you would get these Sato-Tate groups. But we will not follow this approach. Instead, what we will do is to look at certain properties that the Sato-Tate group is expected to satisfy, the Sato-Tate axioms. And then determine which groups satisfy these axioms, obtain a list of groups, and then among these groups check which of them actually arise as Sato-Tate groups of abelian surfaces. So let me start with a proposition. I will still follow the convention for notation, the convention for citation of references of yesterday. So this is a joint work with Kiran Kedlaya and Victor Roger and Drew. And in fact, this proposition relies a lot on a work of Kiran Kedlaya with Banaszak. And it says the following. So imagine you have an abelian variety, A, defined over a number field F of dimension at most 3. Then the Sato-Tate group of A, which is a real Lie subgroup of the unitary symplectic group of degree 2G, satisfies the following properties. The first one is that there exists a homomorphism, theta, from U1 into its connected component that sends, say, an element U to a diagonal matrix that has G elements on the diagonal equal to U and G elements equal to U bar. And the second property is that for every connected component, C of the Sato-Tate group, and for every character, chi of GL to G of C, the expected value of chi of G with respect to the Haar measure mu of the Sato-Tate group over G's belonging to this connected component is an integer. Okay, so I'm already using this notation because maybe I could write mu of chi and times the characteristic function of the connected component, but maybe this is more suggestive. And well, I will speak a bit more about these two properties tomorrow, in the sense that this one, you should see it as a consequence of the fact that the Mumford-Tate conjecture holds for abelian varieties of dimension up to 3, and this property is a consequence of the fact that the algebraic Sato-Tate conjecture holds for this kind of abelian varieties. I will speak about this tomorrow. This is the point on which we rely on this work of Kedlaya and Banaszak. And well, the first remark here is, well, that the Sato-Tate group of A is conjectured to satisfy these two properties. For any G. Okay, let me look at an example. So if I just impose these two conditions, how many groups do I get in when the dimension is G equals 1? Well, the first condition tells me that a group of this shape should be contained in the Sato-Tate group. And, well, of course, one option is this group itself, and another option is whole SU2, and there is just another option, which is the normalizer of this group inside SU2. So I call this T. This is what I was saying yesterday at the end of the talk. So I just get this normalizer of T in SU2, and this is just the group generated by T and a matrix of this form. So up to conjugation, I just get these three groups, and observe that in fact here I've only needed the first condition. The second condition will be crucial later, but in dimension 1 you don't even need it. And as we saw yesterday, this corresponds to the case of an elliptic curve without complex multiplication. This corresponds to the case of an elliptic curve with Cm defined over F. And so that was the remaining case that we did not consider yesterday, in which we have an elliptic curve over F with Cm, but this Cm is not defined over F. Okay? Okay, so you have. I will explain this in a more complicated example, but let's do the argument also here. This has to be contained in the Sato-Tate group. Then, of course, this will work. But then you first analyze which are the possible connected components. And for the connected components, you only have these two. This follows from Lie theory. And then, with these connected components, which groups could arise? Well, the groups with this connected component must be contained in the normalizer of T. And and then you compute the normalizer of T, and you can see that this T has index 2 in this normalizer, essentially because the automorphisms of the U1 are just 2. The identity and complex conjugation. So you have that this index must be 2, and so this is just 1. Mm-hmm. We will do this in a more complicated case. Mm-hmm. Condition 2? The first one. If it's a strong, well, it rules out all finite subgroups, for example. You have many, infinitely many finite subgroups inside, and they cannot arise. It contains a copy of U1. Mm-hmm. Well, with particular eigenvalues. This is also crucial. There must be G equal to U and G equal to U bar. Mm-hmm. So a natural question now is, how many do arise if I consider dimension 2? So that's the theorem that Drew stated yesterday. And it's that up to conjugacy, there are 55 subgroups. Satisfying the two previous conditions. And the possible identity components so the connected components of the identity are 6. So in dimension 1 we had 2. And I'm not going to write the 55 groups, but I will just tell you that this case, the number of groups that we have for each connected component, and in this case we get the most groups, up to 32. In this case we get 10. Two, and of course in this case we just get 1. Nothing can be bigger. So combining this theorem with the previous proposition, what we have is that there are at most 55 possibilities for the Sato-Tate group of an abelian surface. And what I want, and the proof of this theorem is a problem in the theory of Lie groups. And ideally what I would like to do is to give you a proof of this theorem. But it is a bit too long for a talk of 1 hour. However, there is a very similar result with a completely analogous proof, which is slightly simpler. And then what I will do is to state this result and prove this result. Okay? So In fact, what I'm going to do now is simplifying our life. But before doing this, I will complicate it a bit, but keep faith that in me that it's just to simplify life. So I will have to state the Sato-Tate axioms in general. You can find these in 3, but you should, of course, look at the book of Serre lectures on NXP. You can also, it's also there. So what do? You fix a weight W and Hodge numbers HPQ for each pair of integers PQ that add to W. And then write M for the sum of these Hodge numbers. Then the Sato-Tate axioms that I will denote for short this way. For the group G, and relative to weight W and Hodge numbers HPQ are the following. The first one, there exists a homomorphism theta from U1 into so this is the second. I wanna be the second. Yes. So the first one is the G is a closed subgroup of USPM if the weight is odd. Okay? And it is a closed subgroup of the orthogonal group if the weight is even. Okay? Now I can state the second one. Second one is what I was saying. There exists a homomorphism theta from U1 into the connected component of G. I see this G already inside of USP or into the orthogonal. Such that the image of an element U has eigenvalues U to the P minus Q with multiplicity HPQ. And moreover, the conjugates of the image of this homomorphism theta generate a then subgroup of the connected component. So this reminds you a lot of the first condition, and what I will write now is the equivalent of the second condition. It's almost the same for every connected component of G, connected component C of G and character of GLM of C, the expected value of chi of G under the Haar measure of G, and G over this connected component C is an integer. Okay? So there was a question before, how much restrictive is that first property? Well, how much restrictive is this equivalent of the second property? Observe that the key thing is in asking this, G in the connected component. If I just write this integral over G, this is just the multiplicity this is the multiplicity of a character in the group G. So this is always integer. So it's this that it's really meaningful. So some remarks. If A is an abelian variety of dimension G, then the Sato-Tate axioms relative to weight 1 and Hodge numbers H01, H10 equal to G are conjecture to hold. And if the dimension is at most 3, they hold. Okay? So is there any question? Yeah, okay. I didn't want to state it twice, but here it should also be true that the conjugates of this embedded U1 generate a dense subgroup of the connected component. Maybe, okay. I will, let me just put a name to this image. It will be the Hodge circle, okay? I will refer to this image by the Hodge circle. So no, I want for this for the ones that this HP is non-zero, no? So M is the sum of these Hodge numbers. So I'm lying inside matrices of size M times M, and I have some M eigenvalues, and I want them to be of this shape with this multiplicity. So another remark, okay, is that in Serre's article, Propriété conjecturale de groupe de Galois motivique, so we forgot to put this reference in the list of the course description, so that's why I have to write it. He constructs a Sato-Tate group and formulates a Sato-Tate conjecture for motives. And then, if M is a self-dual motive with rational coefficients and weight W and Hodge numbers HPQ, then this group de Galois motivique, this Sato-Tate group of M, is expected to satisfy the Sato-Tate axioms relative to weight W and Hodge numbers HPQ. Okay? So another remark. If I fix a weight W and Hodge numbers HPQ, and let me denote by H the ambient group, USP M, if the weight is odd, and the orthogonal group if the weight is even, then there exists, or up to conjugacy in H, there exists a finite number of subgroups G of H satisfying the Sato-Tate axioms relative to these fixed weight and Hodge numbers. Okay, so I state this as a remark, but okay, it's a theorem. Huh? But then this permits us to look at the Sato-Tate axioms in an almost algorithmic way. So the input is some weight and some Hodge numbers. And then you do some exercise in the theory of Lie groups, and you obtain a finite list of groups. And this is the point of view that we will assume from now on. So you should just, if you want, just look at this as a rather formal or complication. But at the end, what we are going to do now is it's an exercise in Lie groups. So, for example, you could get interested in this weight and these Hodge numbers. Okay, I will not explain why at some point, I don't think it's relevant for this talk, we got interested in this weight and these Hodge numbers, but we did, and then we decided to solve the problem of determining the finite list of groups up to conjugation that satisfy the Sato-Tate axioms for this particular choice, and what we get is this theorem. Up to conjugacy in USP4, there are 26 subgroups. Satisfying the Sato-Tate axioms relative to this weight and Hodge numbers, okay? And the identity component, the possibilities for the identity component are now 7. Are the same 6 that we had for abelian surfaces. Plus the unitary group of degree 2. Okay? And, well, I won't write all of the groups again, but I tell you how many one gets. Of course, here one gets just 1. Again, this case is the one that yields most of the groups. In this case, 10. This gives you 8. Only one, sorry. This gives you 8. 2, 2, and 2. Okay? And what I want to do now is to prove this theorem. Okay? And it will give you the flavor of the proof of the other one. What is happening is completely analogous. Before, though, let me give an example of constructions that would yield Sato-Tate groups in this classification. So for this, let F be a cusp form of weight K and level N and some Nebentypus epsilon that is a new form. So an eigenvalue for the action of the Hecke algebra, and that has rational coefficients. So to it, you can attach a motif, and it is known that this motif has weight equal to k minus 1, so you have the lower by 1 the weight of the cusp form, and has Hodge numbers hk0, h0, k minus 1 equal to 1, and thus the sum m of them is 2. So you can first consider the following construction. So take one cusp form, weight 4, some level n1, trivial Nebentypus, and take f2 to be a cusp form of weight 2 and some level n2, also of trivial Nebentypus, and of course assume that these are new forms with rational coefficients. And then what the construction, it's a direct sum of mf1 plus mf2. And since I want this to have weight 3, this already has weight 3, but here I need to twist by minus 1 to raise the weight up to 3. Okay? And if you look at the Hodge numbers, you will see that they match with this. And another construction, the second one, you take F2, you take F1 first, to have weight 3 for some level, some Nebentypus, and you take F2 to have weight 2. And again, they are new forms with rational coefficients. And the construction that you do here is a tensor product. You consider, oh, maybe I should say something. If the weight is odd and we have rational coefficients, this forces this modular form to have Cm by its Nebentypes. So in particular, this will always be quadratic. In a similar way here, the Nebentypes had to be trivial. Okay? But then the construction that you consider is just this tensor product, and you get weight 2 plus 1, 3, and the Hodge numbers again match with what we want. And okay, I close this parenthesis, and I start with the proof of this theorem. So, sketch of the proof. So how can one prove this kind of results? So take G, a subgroup of USP4, satisfying the second Sato-Tate axiom and the third Sato-Tate axiom. Observe that by saying that it's a subgroup of USP4, I'm already using the first Sato-Tate axiom. The weight is 3, is odd, so it's a subgroup of the unitary symplectic group, and the Hodge numbers at up to 4. So I get here a 4. Okay? So as I said, standard arguments in the theory of Lie groups yield the possibilities for the connected component. And then what we do is to do a proof by case, case by case. So we start with a case that the connected component of G0 is U1. Okay? So what does the second Sato-Tate axiom say in this case? Well, it says that there exists a homomorphism theta from U1 into G as a subgroup of USP4 that sends an element U to a Hodge circle, well, an element U to a diagonal matrix, which has one eigenvalue equal to U to the 3 minus 0. One eigenvalue equal to U to the 2 minus 1. One eigenvalue equal to U to the 1 minus 2, etc. So it must contain this Hodge circle. And, well, I chose the order of these eigenvalues so that this is a symplectic matrix with respect to the symplectic form given by this matrix. Okay? So what are we looking for? We are looking for groups G, of course containing this connected component isomorphic to the U1, and which are contained in USP4. But because of what I said here, again, this, since this quotient is a finite group, this has to be contained in the normalizer, this n is the normalizer of the connected component inside USP4. And in a way that the connected component has finite index in G. Okay? So first thing we do is to compute this normalizer. So first step towards computing the normalizer is to compute the centralizer. So what the centralizer of this connected component? Well, matrices that commute with all these kind of matrices must be diagonal. But well, I want the centralizer in USP4. So I need to impose this Z3, Z4 to be complex conjugates to Z1 and Z2. And if I want them to be unitary, they have to be of absolute value 1. So they lie in U1. So how do I compute now the normalizer? Well, there is a map from N into the automorphisms of the connected component that I can build by sending an element G to the map that sends an H to its conjugate by G. Okay, and what's the kernel of this map? Well, it's those G that go to the map that it's the identity. It's those G that commute with all elements H in G naught. So it's the centralizer. So if I mod by the centralizer, I get an inclusion. And these are, in fact, continuous, no? This is continuous. And remember that this is U, it's isomorphic to U1. What are the continuous automorphisms of the circle? Well, you have just two, as I said before, the identity and complex conjugation. So this is Z mod 2Z. So this tells me that the index of this centralizer in the normalizer is at most 2. And in fact, it's 2 because it's easy to build an element, J, that is outside of the centralizer and in the normalizer. So take, for example, this J. And of course, this element acts on this hot circle as complex conjugation. Good. So we have the normalizer. So let's compute the options for G. And let me first consider the easy case in which G is in fact contained already in the centralizer. Well, observe that this, I've been calling this Z all the time without saying it, but observe that this is clearly isomorphic to U1 cross U1. So if I consider this quotient, what I get is something isomorphic to U1, and then the finite subgroups of this quotient are the finite subgroups of this group, and they are all cyclic. They are generated by roots of unity, no? Finite subgroups of U1 are cyclic. So if I take a lift of such a cyclic subgroup to USP4, what I will get is a group that, okay, contains the connected component and a matrix giving me this cyclic group. And for example, you could take this one. Okay, and well, I will call these groups Cn. And we have obtained infinitely many of them. And I just, at the end, I just want to have 10. But why? Because, well, we still have to impose the third Sato-Tate axiom. So it comes a lemma that says the following. If Cn satisfies the third Sato-Tate axiom, then this n has only 5 possibilities. Okay? So how can we prove this? Well, the first thing you have to do is to choose some character of GL4 of C. Which character do we choose? Well, first let me choose a representation, a very easy one. Just take the identity. And then I let chi to be the character of rho tensored with the contragradient representation. So what's that integral in this case? This chi of g in this case is just the trace of g times the trace of g complex conjugate. So this will be the integral of the square of the absolute value of the trace of g. This is the condition that I will be testing. So the condition of this to be an integer, no? Okay, let me call this matrix zeta n. And then which connected component do I take? I take the connected component corresponding to this zeta n. So I consider the integral of elements g lying in the connected component of the zeta n of the square of the absolute value of the trace. And, well, this is easy to do because we have a parameterization given by this theta of this g naught. So this is just the integral from 0 to 1 of the trace of theta of e to the 2 pi I r times zeta n, absolute value, square. And you can do this computation, and you get 4. Wow, this is not an abstraction. So all these groups for every n satisfy this. If you want to prove the theorem for abelian surfaces, this was always working. This was giving you a meaningful abstraction. Well, no problem. All we have to do is to choose another character. Well, which one we choose? Well, take an integer m and consider rho to this power and the contragradient of rho to this power. Then this character is integrating this thing, and this just gives you that not only the integral of the square of the trace must be an integer, but any power. So we check the next one. What do we get? If we integrate this, well, it's a long, tedious computation, but what you get now is 36 plus 8 times cosine of 2 pi over n. And saying that this is an integer, it's really an abstraction. So this is telling you that this cosine is in minus 1, minus 1/2, 0, 1/2, 1, and this is exactly saying that n has these possibilities. Okay? So one finally can consider the options with G contained, of course, in the normalizer, but not in the centralizer. And what one gets is that they are groups consisting in adding to the Cn the matrix J, that I had here, the matrix J in the normalizer that is not in the centralizer. And so, of course, for n, again in this set, and this gives me, up to conjugation, all the subgroups satisfying the Sato-Tate axioms with this connected component, and they are 10. And, well, you could now consider the case in which the connected component is SU2. But and to see why one just gets one group in this case. But I think I stop here. If somebody's interested, I can do this in the questions.